So the next speaker is Tom Dupre-Latour. I can see you. Can you unmute yourself? Okay, perfect. So it's with great pleasure that I present you Tom Dupre-Latour from the University of California in Berkeley. And he's gonna present his multivariate convolutional sparse coding approach for electromagnetic brain signal. So Tom, the stage is yours. Please go on.
Thank you. So I'm going to present this work that I did during my PhD. It was in Paris, in Telecom and University Paris-Saclay. And this is joint work with Mainak Jas, Thomas Moreau, Umut Simskakli, and Alexandre Renfort. And this is about a way to analyze time series that you may not know because it's not very standard. It's based on a temporal waveform analysis. So what do I mean by that? To take a step back, here is one example of a time series recorded with LFP on a rodent. And a typical way to represent this data is to look at different frequencies or frequency bands. So here, for example, I filter at a low frequency band, and I immediately capture somehow the slow variation of this signal. And you see that it really corresponds to something that varies like slowly. And on the other hand, if I use a high frequency band, I capture these bursts of high frequencies that you can see in the original signal as well. But now you can ask yourself, is this the right representation for this data? And one thing that you can note is that these two are actually correlated in the sense that every time you have a peak of the slow oscillation, you have a burst of the high oscillation. And this is known as cross-frequency coupling or phase amplitude coupling. And this is seen as a coupling because we decompose in this way these two frequency bands. But essentially, this is only one signal. And we arbitrarily decide to decompose in two narrow band representations and then say they are coupled. But this is only one signal, and maybe there is a representation where we can have both at the same time and not like separating them. Another example of that could be in this echoic signal where you have long, like flat plateau and very deep peak here like that. And to reconstruct that with narrow band representations, you would have like this oscillation that really captures the global trend. And you would need a harmonic at twice the frequency where then the trough are aligned so they can like build something deeper. And here you have a trough and a peak, and so it kind of make it flat. And you see here that here again, decomposing the two doesn't fully make sense. Like it is useful in so many cases that I cannot completely discard it, but at the same time, these two are linked together. They are harmonics of each other, and maybe considering the actual time waveform is a better idea. A third example, this is MEG. Here you have a heartbeat. This is maybe not the most useful signal of MEG, but this is something the typical signal you have. Also, if you have a trigger, you can have a very short response. And if you filter it, obviously, because of this very peaky, very instantaneous signal, if you filter it, you will have some kind of ripples like that do not fully represent the signal. So there is a huge literature of an alternative way of analyzing temporal data. And it started with the idea of wavelets. Instead of using Fourier analysis, maybe we could start using some new representations, some wavelets, that better capture some transient behaviors. And in this wavelet basis, the signal is said to be sparse, and the goal is to be sparse in the sense that if the wavelet basis is well defined, you need a very few elements to actually reconstruct your signal. So sparsity is a good sign that your wavelet basis is actually interesting for your signal. And then another step was taken by saying maybe we can learn the wavelet basis instead of trying a bunch of them and seeing which one is the best. Maybe we can learn and use the sparsity as a target. So this is what is called sparse coding or dictionary learning. And this was typically done by taking a signal or an image and decomposing into chunks. And a small chunk of signal, then you would learn a basis on this chunk. But there is no reason that these chunks are well aligned with whatever waveform you are detecting. And so another step was taken to go toward shift invariant representation that are not related to this grid of chunks. And from this, there have been multiple work trying to apply this kind of technique on neurophysiology with a bunch of different techniques. And the one that we are going to present here today is called convolutional sparse coding. So convolutional sparse coding is a way of modeling the signal. Here you have a fake signal in blue. And my assumption would be that I can reconstruct this signal based on two things. The first thing will be a prototypical waveform here that I can sometimes call a pattern or a waveform or sometimes an atom, because it's kind of the building block of my signal. And then the position and amplitude of this atom that will be repeated many times is encoded in this green signal Z, which is 0 most of the time, so which is sparse in this sense. And sometimes there is one point where it's like non-zero, and it encodes the starting and the amplitude of this waveform. So mathematically, what does it mean? It means that n is just an epoch, for example, will be a sum of convolution between my atoms here, dk. I can have k of them too, because maybe I can have a dictionary of different atoms, and I will convolve them with my activation that is specific to this atom and to this epoch, and I reconstruct my signal this way. And here I have epsilon, which is the error, something that I cannot model by my signal, and I will assume that it's Gaussian white noise. So once I have that, I can build a optimization problem to try to learn these components, so the activations and the atoms. And this is a standard formulation with an L2 norm. This is just basically least square. And then I have here a regularization that promotes sparsity in the activations. So this is an L1 regularization. This is what you find in the lasso, for example. And this is to ensure that, or to promote that the activation Z tend to be 0 most of the time and have very few activations. There is also some normalization, but essentially all the model is in this formulation here. So let's try it on the signal I showed you at the beginning. And what we see that it captures, like here I show 3 different atoms, so 3 different dk. And what we see that it captures the slow oscillation, but at the same time, it also captures somehow the cross-frequency coupling. That is the high frequency that is at the top of the oscillation. So this is just walking more or less out of the box, and this is pretty encouraging. And based on that, we explored 3 different kind of challenges that we had to face when using these models. The first challenge, I will go extremely quick, is just optimization speed, because this problem takes a bit of time to converge, to solve. And just to mention quickly, the way we solve that is to alternate between solving for Z and solving for D. So solving for the activations with a fixed dictionary, and solving for the dictionary of atoms, of patterns, with fixed activations. And alternating between the two, we refine and solve the optimization problem. So there have been a bunch of techniques to perform the Z step, a bunch of techniques to do the D step. We propose some different ones, and then we say that we show that we are faster in some sense. I will skip that in the interest of time, but this is just to show you that this is something we also try to push to make the method actually usable. Another challenge is to deal with strong artifacts. And strong artifacts is something you have in real data. Like, for example, the electrodes just lose contact. You have a huge value that goes to the maximum value you can record, and that it clips, and then it goes down and everything. And these kind of artifacts really prevent your model from capturing the true, like the important signal. So here, if I have x hat, the model signal, so the reconstruction, the standard Gaussian way to represent a signal in a probabilistic way is to say that x, the true signal, is follow a normal distribution centered on x hat. So it means that the error between x and x hat, epsilon, this error is Gaussian. This is just a way to reformulate that. And if you look at this blue distribution, this is a Gaussian distribution in a log representation. And what you see is that this Gaussian distribution goes to 0 extremely fast. So if you see in this distribution what is the probability to have a value of 20, for example, it will be extremely small. So if the difference between x and x hat is something about 20, for example, because of this huge artifact you have at a very limited time point in your data, then the model will completely focus on this, because it's so improbable, so unlikely, that it will just change all its representation to focus on this error. And the idea we had at the time was to say, okay, maybe we can use a different distribution. For example, an alpha stable distribution. Here I showed 2 examples with different values of alpha. Alpha equal to correspond to the Gaussian distribution. And this is called a heavy tail distribution, in the sense that it goes to 0 also. It follows kind of the same shape as the Gaussian towards 0, but then it goes to 0 much more slowly. And so if I have a value of 20, for example, it is still probable. It is still, and it will not drive the model crazy. So now the question is, what does it change in the optimization problem? Because Gaussian is known to be easy to use, and alpha stable is harder. Especially, we don't have a closed form solution for the alpha stable distribution. So what we used is a conditional formulation, where it is actually Gaussian, but with a different phi, a different standard deviation of the Gaussian for each time. And this phi is estimated also with a alpha stable distribution. So basically, it's not Gaussian anymore, but it's conditionally Gaussian, conditionally to this standard deviation that we have to estimate. So basically, how can we solve this optimization problem? we will do a Monte Carlo expectation maximization algorithm. And this algorithm is alternate between an E step, the expectation step, where we estimate phi as the standard deviation at each time point of the Gaussian noise model, and a weighted CSC, a weighted convolutional sparse coding, where you have exactly the same model as before, except we have now a weight associated at each time point that will downscale the moment in time where you have an artifact. So it's a bit quick. I'm not going to go too into details because it's a bit technical. But in practice, this is the kind of result we have. And here, this is a figure I already showed you with the 3 atoms on the LFP signals. And this is done without artifacts, which means that we manually removed the moment in time where we had artifacts. And if we add back the artifacts because we had for example, no opportunity to remove them or something, then it completely changed the result, because now the atoms only focus on the artifacts. And if we add back the artifact, but we use the alpha stable distribution, then we are robust to these artifacts, and we can recover something that looks very similar to the previous result. So this is something we published at NeurIPS in 2017, and I think that this is something that could be extremely useful if you have artifacts that are hard to remove. But to be completely honest, if you have very strong artifacts, maybe you had a better deal removing them by hand, if you can, and then use the simple version here, because you will save you the trouble of doing the Monte Carlo expectation maximization, which is encoded in an open source package I can give you, but I will give you at the end of this talk. But it's much simpler to just use convolutional sparse coding. So this is why in the third challenge I'm going to present, we completely ignore this trick to deal with artifacts, and we will just use a regular convolutional sparse coding. So in the third challenge, what we wanted to do was to apply that on MEG, like on multivariate like signals. And here is an example of MEG. You probably know it. This is multiple channels, and you see that the same information is captured multiple times on multiple channels. So it's pretty redundant. And we'll see how to actually use that to make a model that is more powerful. So first, let's change our model. We have this model where X was univariate, only one channel, and now we have multiple channels, let's say 100 channels. Then we just need to change the atoms to be not only over time, but over time and channels. And so here now you have 2D, but the activation are still just temporal, and the convolution operation that is here will apply only on time, and it will just copy the same activation on all the different channels. So this is a reasonable way to do that. But as I said previously, if you have some source, some dipole in the brain that creates some kind of waveform, then it will be picked up by many different channels. Maybe not all of them, but many of them, and maybe with different amplitudes or maybe different polarity. But essentially, it will be captured over many channels. And the question is, how can we use that in our model? And the way we propose to use that is to change each atom to be rank 1. So it means that it's now an outer product of 2 one-dimensional vectors, and U will correspond to the temporal vector, the temporal waveform that we see here, for example, and V will correspond to the spatial pattern over channels. So how this particular waveform is spread over channels and with which amplitude and which polarity. So now we have an optimization where we need to solve the three, U, V, and Z, but it's not so more complicated. And this rank 1 constraint has different advantages. The first one is that it's very consistent with the physics of electromagnetic waves. So this is an electromagnetic waves is so fast at the scale of the brain that it is essentially instantaneous, and that the signal is really propagating over all channels instantaneously. So it is pretty consistent with the physics. But another advantage is that it scales differently with the size L and P. And here, L is the size of U, the temporal atom, and P is the size of the number of channels. And if we had like a full size matrix, L times P, it would mean L times P parameters to estimate, and also so a less robust estimation, but also a longer estimation. And here, because we use only L plus P, L in U and P in V, we have something that has less parameters, more robust to estimate, and also much faster to estimate. So this is what we published in NeurIPS 2018, and I think this is a very reasonable way to apply this convolutional sparse coding to the multivariate case. And to give you some example, they are not in the paper, but they are on the website online. This is 4 examples of the spatiotemporal atoms we have. We have here a spatial pattern, which is V, and the associated temporal pattern U, and these correspond to the heartbeat. So you can see pretty well the waveform of the heartbeat. And you can see that if you wanted to filter it, this is the pore spectral density of the temporal pattern. And if you wanted to filter it, you would need to filter a very extremely wide band. So this will just linear filtering. Here is another pattern that is well extracted as well. Is associated with the eye blinks. You have here the pretty prototypical waveform. And here you have 2 other examples. The first example is something that is related to the trigger of the experiment. So that is well located in time. And another pattern here that is a more sustained rhythm that is located here in the occipital. And this is what sometimes is called a mu rhythm. This mu rhythm is because of the shape of this rhythm, which is a bit asymmetrical. And to capture this mu rhythm with filtering, you would need to filter at different frequency band, because the way this is built is that in frequency is that it is not only at 8 hertz here, this blob that correspond to the main oscillation, but there is also a harmonic, pretty strong harmonic at 16 hertz and even at 24 hertz. And this is because we consider mostly time and not the Fourier domain, that we can capture something that has components over different frequency bands. So very quickly, I will show another thing we can do. For example, this is 3 different atoms that I handpicked, and what I show here is 4 different events that happened in this dataset, and show the activations of these atoms over the locked with the timing of the different 4 events. So you have 3 atoms and 4 events, and this is, for example, the activation of the first atom related to the first event, and you see that it immediately follow the first event in a pretty consistent way. and in this data set, for example, the third event, this second atom also follows the third and fourth event, and this one follows the fourth event only. And if you look, so this is showing that these atoms are related to the different trigger, but we can go a bit further and show this is the fourth event. I will look for more specifically at the third and fourth event. And these are the different epochs. So this is the raw data just aligned to this trigger at time 0 and coded in blue and red. And this is evoked, so the average of the different epochs in blue. And in red, it's the approximation of the reconstructed signal with only 2 atoms. So with only 2 atoms, the 2 that I showed you here, this one and this one, you can actually reconstruct a lot of this trend, a lot of what's happening, and you can actually determine precisely what is the timing of like the activation of this atom. And you see that this timing can actually be a bit dependent. It's not always the same delay between the trigger and the moment this atom is activated. On the other hand, here in this event 4, you also have a pretty good reconstruction with only 2 atoms, but you see that there is a second atom that is much more activated and much more consistent in terms of delay between the trigger and the activation. And then you have the second atom in orange that is activated a bit later and with also a bit more variation. So this is just not concluding anything with this particular data set. This is an example of what you can do with this kind of model, that you can not only extract the atoms with their spatial and temporal components, but also look more precisely at their activation and how they relate to your experiment. So to conclude, this is presenting something called, as we call, temporal waveform analysis in contrast with the Fourier kind of frequency analysis. And we use convolutional sparse coding. Convolutional sparse coding it's a well-posed optimization problem. So it has a lot of good mathematical properties, and it's reasonably easy to solve. I showed you some extension for more robustness to strong artifacts using an alpha stable distribution. I showed you also how to extend that to MEG like signals with a rank find constraint. And we spent a lot of time actually proposing an open source implementation of that. We spent a lot of time writing a unit tests, extensive documentation, and a gallery of examples to ease any potential user to learn and to try this technique on their data. So this is the website. It's on GitHub. It's open source, and you are very welcome to try it and open some issues or comments if you require some help. So thank you very much.
Okay, thank you, Tom, for this very nice and interesting talk at Virtual Club. I think we have time for a couple of quick questions from the audience. We have a question from the chat. Gian Vittorio is asking if you have never tried this approach, for example, to detect epileptic spikes.
I have not tried, no. Unfortunately, I think that I had not so much time to try to apply this on so many great data sets. We had some very limited data set, and I would be very curious to see what it gives for epilepsy. Yeah, that's a very good idea.
Okay, other questions from the audience? Okay, if not, I thank again Tom for this very nice talk. Another virtual club.
Thank you.